Hello my dears, here is week number 13 material, where in this material we are going to study some of other measurements like flow measurements, level measurement and displacement measurement. Flow measurement. In the flow measurement we are measuring the flow of bulk fluid, or the movement of bulk of fluid is considered as a flow measurement, which very much needed for the industry and the quality control or operation of continuous process and so on. In engineering, the volumetric flow is given a sample of Q and the mass flow given the sample of M. Flow measurement find application in transportation of a fluid, gas and water supply system, irrigation system, and industrial process control. In a flow measurement, we are going to consider the flow rate and the total flow, where the flow rate is the volume of fluid passing a given point in a given amount of time. So if I assume this is the pipe, this is the point, the amount of liquid passing this point over period of time or over a specific time is known as the flow rate, and its unit is given as gallon per minute or cubic feet per minute or liter per minute. So whenever we are mentioning per minute, that means we are talking about the flow rate, but the total flow is the quantity of flow over a period of time, the total quantity of flow. That means if the flow is passing to, for example, certain tank, so we are going to say the quantity of the water in the tank is, for example, 1,000 liter, 100 gallon, and so on. So that means the total quantity regardless of the time factor, because it's over certain period. In the flow formula, he's saying if the flow rate in a system is not changing with time, we can write the flow rate as Q equal to V into A, where Q, of course, is the flow rate as mentioned earlier, V is the average velocity, and A is the cross-sectional area. So again here, I can consider the flow rate as Q equal to the cross-sectional area of the pipe multiplied into the velocity. Now, how about mass flow rate? Mass flow rate is different, because mass flow rate is having relation with the flow rate, where the relation is, or the mass flow rate, which given as F, it's can be related to the flow rate as F equal to rho into Q, where rho is the density of the liquid. So that means the flow rate is considering the liquid density factor, considering the factor of the density of the liquid in the flow rate. In the flow formula, if the flow is moving or going from bigger cross-sectional area pipe to smaller cross-sectional area pipe, how can we relate them to each other? In this equation, he's showing us that the flow rate will remain the same. The flow rate will remain the same, means the Q in the first pipe is same as Q in the second pipe. That means some of the factor, if any of the factor change, the other factor will change as well to keep the two equations balanced. What he mean here? He said V1A1 means the velocity of the first pipe into the cross-sectional area of the first pipe is equal to V2, means the velocity of the second pipe multiplied into the cross-sectional area of the other pipe. If you look at this figure, for example, in this pipes, you will find as we are moving from the first part, I mean this part, to the second part, the cross-sectional area is getting smaller. So now we can understand out of this that the velocity will be higher. As a result of that, velocity will be higher to keep this side balanced with this side or equal to the other side. Here, very simple example, you can just apply it. It's example calculating how the quantity is going to change. So let us read it and see. A pipe goes from 9 centimeter diameter to 6 centimeter diameter. So if I consider this one, He's saying here that this diameter is equal to 9, where this diameter is equal to 6 centimeter, and the velocity in the 9 centimeter is equal to 2.21 meter per second. So here v equal to 2.21 meter per second. What is the velocity in the 6 centimeter section? That means he wants to know what is the velocity here. I think it's very clear that as we are moving from bigger cross-sectional area to smaller cross-sectional area, the velocity will be higher here. So when you substitute the quantities in this equation, considering that we need to calculate the area of the first one and then the area of the second one, then V is going to be the same. Calculate V2. V2 is equal to V1 A1 over A2. When you calculate it, you are going to get a value of V2 bigger than 2.21. Now we will start thinking of the measurement, where we are going to talk about the flow measurement. In the measurement of a flow, we are not measuring the flow direct. The flow is to be measured in indirect way. Like what? Like measuring the pressure, which can be compared with the flow rate. So we can calculate even the differential pressure, which will tell us about the flow rate. What are we measuring in the flow? I mean, in terms of a flow, what are we measuring? We are measuring the flow rate. I mean, the sensors which we are going to use to measure the flow. Used for what? They are used to measure the flow rate or the total flow and the mass flow. Now, what kind of sensors we are going to select and based on what? The kind of sensor to be selected based on the type of material to be measured and the accuracy we are looking for. The type of material means whether it's liquid or gas or even solid. So, and also it's affected by the temperature of the material to be measured, whether the material to be measured is conducting or non-conducting. So all of these factors are going to tell us which sensor to be used. Here are three common principles of volumetric flow measurement: differential pressure measurement, and rotating flow and electromagnet. So here there are three techniques used to measure the flow: differential pressure, rotating flow rate, and electromagnetic flow meters. Let us see them one by one after this to understand the principle of operation of each of them. Here is the differential pressure measurement. In differential pressure measurement, we are going to allow, or we are going to make a differential in pressure for the liquid as it's flowing through certain pipe. So we are going to let the flow go through certain pipe, and that pipe will generate differential pressure between point and other point. And we are going to measure that differential pressure by differential pressure sensor, which will tell us about the flow rate. The types of pipes used for that are Venturi tube, flow nozzle, dull tube, and elbow. They are seen in the next slide. Here are the pipe I'm talking about. So the Venturi tube going to have different pressure between this point, this location, and this location. So you look at its arrangement, and if I measure the pressure at this point and the pressure at this point, we will find that they are different. So the difference between the two pressure is going to tell us about the flow rate. Same thing for the others. Notice here there is P high, P low. So always we are having, due to the arrangement of this pipe, we are going to have a point of high pressure and point of low pressure, and we are going to measure the difference between the two pressure, which will tell us about the flow rate. Same thing here, high pressure is here, low pressure is here, and for the elbow also, high pressure is here and low pressure is here. So always we are going to connect differential pressure between this point and this point, which will tell us about the flow rate. In terms of rotating flow rate device, here we are going to have a kind of rotating element which will rotate due to the flow of the liquid. Let us see it in the next slide. So here is the pipe. This is the rotating flow device where the flow is going to go here in this direction. Let's say this is the flow where the liquid is going to flow in this direction. So now as it's flowing, it's going to rotate this blade. Now the speed of rotation or the number of turns for the blade is telling me about the flow. Now, just to let us be clear about this point, usually how to get the measurement out of this value, because what kind of electrical signal going to be generated out of that? Remember, we are having sensors here. We are dealing with sensors. If sensors means we are converting the quantity to electrical quantity. In the differential pressure sensor, which we measured earlier, or the method we discussed earlier, is going to convert the flow to differential pressure, and the differential pressure sensor will convert it to electrical. Here, the flow going to be converted to rotating part. So how am I going to consider it as, or how am I going to convert it to electrical signal? Of course, we can use the blade from ferromagnet material, and we are going to get a magnetic sensor here at this point. This is magnetic sensor. So each rotation for the blade, let's say there is a magnet here, each rotation for the blade is going to get the magnet to the magnetic sensor. So the sensor going to measure on, off, on, off means signal, no signal, signal, no signal. So of course, the frequency of this signal is going to tell me about the flow rate. It's as simple as this. The frequency of the signal will tell us about the flow rate. This device is considered accurate. The device or rotating device considered accurate with a good flow operating and temperature range. That means it can operate for bigger range. So for the fluid to be with higher temperature, we still can use, or we can use this kind of sensor. Electromagnetic flow meter. This kind of sensor is to be used when the liquid is conductive. When the liquid to be measured is conductive. If it's not conductive, we cannot apply or we cannot use this kind of sensor. Because this kind of sensor depending on inducing voltage and measuring the voltage. So if the material to be measured is non-conducting, it's not going to make any voltage induced in it. Let us see it in the next slide. Electromagnetic flow meter, it depends on Faraday's law, or we will consider Faraday's law while thinking of it. What Faraday's law said? Faraday's law said if there is a magnetic field, this is poles, south and north, and if a conductor, this conductor, cut the magnetic field, I mean it moves up, and it cut the magnetic field while moving on a velocity of certain quantity, there will be voltage induced in this conductor. And the voltage induced in the conductor to be calculated from this formula. E equal to B into L into V, where B is the flux density, which caused by the permanent magnet. L is the length of the conductor. Let me put it with its color. The length of the conductor. V is the velocity of cutting. So there will be a voltage generated if this situation happens. Why or how am I going to use this idea here? I'm going to use this idea in the flow measurement as the conductor we are talking about is going to be certain slot of the liquid flowing. So I will assume the liquid part, or I'm going to take this part of the liquid. This piece is moving. Again, this is a piece of the liquid flowing. The piece is going to move in the pipe. So as it's moving in the pipe, it's going to go to reach this area. This area is coming between two coils, this coil and this coil. The coils are excited by voltage source, which going to result in magnetic field here, magnetic field here. So if you notice, that slot or that piece of liquid is going to pass through the magnetic field. And since it's moving with certain velocity, there will be voltage induced in it. So this piece, the piece I'm talking about, will have voltage in it. Remember, I said this sensor to be used only for the conducting liquid. If the liquid is non-conducting, we cannot use it. Okay, after this stage, that quantity of, or that piece which I'm talking about, the piece of my example, is going to reach to this location. It's reaching this location, where in this location we are having electrodes linked to it, linked to the pipe. So they are going to measure the voltage inside this piece. Okay, and the voltage to be measured by the voltmeter here. Now the voltmeter here going to measure the voltage induced in the liquid. I hope you catch the idea. What makes the voltage induced in the liquid? It's due to passing through the magnetic field. Now, passing with certain velocity. I can say here, with consideration to Faraday's law, the only parameter will affect the quantity of voltage generated or the quantity of voltage measured is going to be the velocity, because B, the flux, is going to be the same. Flux is not going to change. And L is the length of this piece, the piece I'm taking. The length, which means it's the diameter. It's the diameter of the pipe. So the only factor remaining is V. So only the velocity is going to be measured in this case. So E representing the velocity. The higher E, the higher the velocity. And remember that the higher velocity, that means the higher the Q, which means E here is proportional to Q. The higher E, it tells me that the flow rate is higher. That's how we can measure the flow rate in terms of keeping or considering Faraday's law. But I will repeat again and again, this kind of sensor to be used if the liquid to be measured is conducting.